Okay, I always seem to go at the end of these talks, these sessions. I think that's because beer is served right afterwards, so they know I won't go overtime. So what I'm going to talk about is a work in progress, and actually it's not so much my work as it is my co-author, Madeline Peters. She finished her senior honors thesis in February, gave it to me and said, what else can I do? So we started this project in February where we picked up on something that Jen Eisen and Emily Austin got a little bit of a start on before they got bogged down with their main projects. And so she picked it up, and what we're talking about is relating two things about non-random mating or departures from panmixia and how that affects population genetic structure. So I'm going to start by going over some ideas from Sewell Wright on how you can get genetic structure building up in populations even if they occupy a uniform landscape. And then ideas about how assortative mating for mating phenology can end up giving a temporal structure, at least to loci involved in mating time. And then we're going to look and ask some questions about, well, how can these two things interact with one another? Okay, so if you look at this, imagine that you have a uniform landscape occupied by a number of individuals. You see here 3 different genotypes at a nuclear locus, and we have this central individual right here. This circle down here, that's its mating radius. So if you can sort of think of this, as I always think of things, as being a hermaphroditic annual plant, in this case a self-compatible one, it can exchange pollen with anybody within this radius, okay? And that's an area that the number of individuals inside that radius is what Wright would have called the genetic neighborhood, and the number of individuals in the genetic neighborhood is equal to this, where we have 4 pi times the variance in dispersal distance, of in this case of pollen, times the density, and that's the number of individuals that you can think of as being in the mating pool, okay? Now, if you have a large distance that you can exchange pollen in, then what you have is a situation is where the size of the genetic neighborhood is about the same size as the entire population, the census size of the population, and you have a situation in which then the effective population size is about the same as the population size of the total population, assuming that everybody can mate with everybody else and things drift at the rate that you would expect for the population size, census size. If you imagine, though, a smaller genetic neighborhood where you have only a few individuals which can mate with one another, what you have is the neighborhood size is smaller than the total population size. And what you find is that over time, if you have these little neighborhoods that start out with, by chance, similar genes clustered together, you can get a bigger and bigger clustering going on. And each little neighborhood, yes, undergoes drift, and undergoes drift at a high rate, but they drift in different directions. In the end, you get to the situation where you have each neighborhood drifting to some neighborhoods drifting towards fixation of one of them, one fixing to the other, so the whole ensemble drifts at a rate that's lower than what you'd expect for the census population size. So the effective population size actually exceeds total population size. So what we want to go on to next is, well, let's think, how does genetic variance in mating phenology affect temporal structure in the population? So imagine then we have this situation where we have 2 alleles affecting flowering time, and we have late flowering genotypes down here, early flowering genotypes here, and intermediate right here, okay? If you look at this, if we assume a situation in which assortative mating is perfect, then what you would get is a mating pool down here, so that you have little a, little b homozygotes mating with one another. What do they produce? Little a, little b homozygotes. Up here, big A, big B homozygotes. But in this band right here, they all are phenotypically the same. When you mate within this mating pool, you're going to get some individuals that some of the offspring will be back in this intermediate phenotype, okay? But you're going to get some of them that actually end up in this genotype, some of them end up in this genotype. So the offspring coming out of this mating pool get recruited into these extreme mating pools. That then increases the genetic variance, and you can actually end up in a situation with perfect disordered mating within just about 10 generations, ending up into just 2 genotypes like this, and you end up, you notice what you get is linkage disequilibrium. That is, if you get a little A gamete, it's going to have a little B gamete, or gene in the gamete too. If there's a big A in the gamete, there's going to be a big B in the gamete. So you have this gametic linkage disequilibrium, and you can actually get then isolation by time, in this case, perfect isolation, okay? How do these two things interact? Well, let's look at this situation. Now, instead of looking at neutral alleles, we're looking at a bunch of flowering time genotypes across the uniform landscape. We're sort of saying, here's the pollen dispersal distance, okay, and we're sort of asking, what's the size of this genetic neighborhood? Well, there's 17 individuals in that neighborhood, but if they're not flowering at the same time, there's not 17 individuals in that genetic neighborhood. There is, in fact, 5 individuals in that genetic neighborhood. So that's at the beginning of the season, the 5 early plants in that circle can mate with each other. They can't mate with the others. At the end of the season, the 5 late genotypes here in this one mate with another, not with the earlier individuals. So that you have then the possibility that by adding and layering on top this temporal isolation, that you actually decrease down the neighborhood size, and you have the potentiality that this isolation time actually accelerates and amplifies the effect of these limited spatial dispersal of pollen. Or do you? Okay. Remember we said that when you're looking at neutral loci, you get spatial clusters. Do you start getting clusters in flowering time genes, and actually do you end up filling things up so that you get clustered things together? Okay, so then you can also ask, what's the consequence for neutral genes, neutral alleles, neutral loci? Okay, so this is that same thing we had before, except instead of looking at 9 genotypes, we're looking at 27. Okay, so we just added then a neutral locus here. And if this is the population starting out at multi-locus Hardy-Weinberg equilibrium. And so if you look at these 3 little bubbles here, these are all little a, big B homozygotes, and then they are then divided up into genotypes that include big Z, little z, and a heterozygote. Okay, so that's everything starting out at equilibrium. If you have just this temporal sort of mating going on, and you have a spatially well-mixed population, so it doesn't matter how far away you are, you have an equal probability of exchanging pollen. The equilibrium solution would be something like this. In other words, you've got this linkage equilibrium increasing the variance in the flowering time alleles, no effect on the neutral alleles. This is a well-supported theoretical. Dan Gino will work this all out, so I think I'm right on this. Okay. But then the question becomes, well, what if, though, you get instead of having a spatially well-mixed population, you have this occurring in a population that is not spatially well-mixed, in which you have very limited dispersal of pollen. You can get something. You can get darkness, my old friend. You can end up getting that you have small neighborhood size, you get local inbreeding, and you end up then getting these pockets, and you lose the heterozygotes as one little pocket drifts to fixation for one allele, another little pocket goes to fixation for the other allele. Or Another more extreme possibility would be that you actually end up getting linkage disequilibrium between the neutral locus and the flowering time locus if somehow things get just dragged around with one another so that you get things drifting off to fixation in particular spatial temporal groups one way or the other. Okay, so that's the idea. So the questions that we wanted to ask in a simulation was, does the limited dispersal lead to spatial clustering of flowering time loci? Because if it does, that will then counter. If it does, it may counter the effect of the temporal isolation. Are flowering time clusters sufficiently small and temporally isolated to slow the loss of drift at neutral loci? And does the temporal isolation enhance the spatial structure by promoting linkage disequilibrium between flowering time and the neutral loci? So it's just a simple simulation that we did where we had an n by n grid, one plant at every point on the grid. There was 5 flowering time loci that we looked at. Actually, it was 10 neutral loci that we looked at, unlinked, kept track of individuals generation after generation. Every individual on the grid was assigned a mating probability to every other individual on the grid. That mating probability was determined by the distance and their overlap in the flowering schedule. They generated then an offspring. We had Mendelian inheritance. The seed landed somewhere close to where the mother was, and then you end going through this loop 500 times. Okay. Again, the mating probability was this, how close they are, how far they are apart from other, how much they overlap with their flowering schedule. Okay, I'm going to show this. Okay, if you only have isolation by distance alone going on, here's what it looks like. Things are just sort of drifting, right? If you have only isolation by time going on, this is just a sort of domain. You don't see really any pattern in here. You're getting more and more extreme genotypes due to a sort of mating, but there's no spatial clustering. But if you have both of these things going on, you start getting spatial clustering. Individuals that are close together have similar flowering times. Further up here, similar flowering times. These guys are late, these guys are early. You get the spatial clustering. What happens at neutral alleles? Well, here we see what's an example, neutral locus, and what you see here is not much apparent. You get drift, you see drift going on, but you don't see much apparent clustering here. Okay, if you look at what's the variance in allele frequencies, so in other words, over the 500 generations, in other words, as you go down this way, you're talking about stronger genetic drift. If you're looking at the flowering time loci, what happens is if you assume that the flowering time does not induce assortative mating, you start losing genetic diversity if you have high density populations, a large genetic neighborhood. If you have a low density population, a low genetic neighborhood size, you don't lose diversity very much. That's like Wright's prediction, okay? And even when none reproduce that. Okay, for flowering time loci, what you find is that you end up, by doing this clustering, you lose less diversity in the flowering time loci over time. Here's what you get for neutral loci. This has no effect on neutral loci. We're fine. Okay, so the answer that I can give you is that you don't get temporal clustering. It does not affect the loss of diversity of neutral loci. Although, if you look at this, and this is in space and time, you look, these individuals up here might be right next to these individuals down there in space, but they're greatly distant in time. And what we do find is that over the course of 500 generations, if you look at these neutral loci, that their spatial autocorrelation among neutral loci is low, doesn't increase much over 500 generations. But if you look at this 3-dimensional autocorrelation using all three dimensions, not just space, but time, you'd start getting clustering in 3 dimensions of these neutral loci, which kind of implies that you get these neutral loci going into linkage disequilibrium with the flowering time loci. Not sure what the consequences of that are in the case of neutrality, but you can imagine that this could be important if there's selection going on to those background loci. So here's what we've got with this so far. Again, we started this at the beginning of March. Madeline was mailing the output on Friday, so we're still got a long way to go, but we'll just say thank you to a bunch of people that helped out. And if you are interested in finding out some of these, talk to me or anybody else from the University of Toronto. Okay, thank you.